Okay. So, most of these are already told to you probably for the last 2 days. So, but just to get into the mode environment, I will just summarize what it is. So basically our idea is to teach students who are coming after 12th, right, and usually whoever joins after 12th for engineering degrees and everything, their courses can be broadly classified into 2 categories, right. One where they do courses in common with everyone, which are the basic courses, which will help them to do their professional courses when they go to their respective department courses, right. So, these talks, I think what Professor Harbola gave and what I will be speaking and what Professor Rao will speak tomorrow is about the science core courses, which they are going to teach the first years who are going to join after JEE exam. Okay. So, of these core courses, of course, the main thing is physics, mathematics, chemistry, of computer science, all these things, and yesterday you must have seen computer science by Professor Surendra Baswana, who was telling you how to teach those courses. So, I am going to focus on the core mathematics program, which we teach the UG students for all the first years and up to their 3rd semester basically. So, this is how we divide the mathematics course for the first years and the second years. So, in the first semester we teach them calculus and geometry, this is how we divide it. So, in the first semester, and in the second semester linear algebra complex analysis, and then ODE and PDE in the 3rd semester. After this they usually start doing their respective department courses. Okay. And the order is very important. I mean, here we have divided the course in such a way that, so they come after 12th, where should they start? We take them slowly up to say ODE, PDE part, and then they can split among themselves. So, just to give you an idea of how, I mean, how a semester here at least. So, here I should warn you that when we teach these courses, we teach to 840 students, which may not be the case with you and so on. So, we have other constraints which we need to take care of, like for instance, I mean, of course, now we take attendance using some biometric and so on, but imposing marks for attendance in those big class 840 students, in fact, I won't even know them personally. If it is 30, 40, I can call out names, okay, you tell me this, you tell me that. 840, there is no way, and in fact, we do not even have a lecture hall which can accommodate 840. So, it is in that sense. So, we are actually teaching a large number here, but finally, the lecture content is not going to change, whether I am going to teach 1 student or 800 or 1000, whatever I am going to speak is going to be the same. So, that way everything is common here. So, here in a semester we approximately have 40 lectures spread over 14 weeks, which is say from Jan to April or from July to November, right. And because these are first year students, just teaching, lecturing and going is not going to help them much. So, we have to actually see that they are actually being trained every week. So, we have this assignment session, weekly assignment. So, the weekly tutorials which we have every week, which so we actually circulate this assignment sheet beforehand, because we actually plan our lectures beforehand. So, we know what we will cover in a week. So, we prepare problems based on those lectures well ahead, and then can circulate these assignments before, and then they are supposed to do that, and in the following week so the first tutorial they are going to, so we discuss with them how to solve these problems and so on. This is how. So, in a 14 weeks we usually have 14 assignments, and we have approximately 40 lectures, which is comes to say 3 lectures per week and so on. And how do we evaluate them? We usually have minimum 4 exams, right. I mean, so basically, so this spread over say 4 months. So, 1 exam every week, which is kind of we check how much they understand, they do not understand and so on. Okay. And we also tell them at the beginning of the semester beforehand what we will follow in the course, what we will teach, what we will not, what are the rules and regulations of the course, like, so how much marks is assigned for each part of the exam and so on. All this we are done, and these things must have been discussed to you already in some sense. Okay. So, now let us get into the mathematics part. So, as I said, the first semester we teach calculus and geometry. So, this is the content which is, so which might be similar to what you will be teaching. which is the calculus part. So, here if you see up to this part, up to this part is the calculus, and then comes the geometry part here, okay, split like that. And if you actually see, they are actually split almost equally. From here to here, this should cover up to 20 lectures, and from here to here, there should be some 20 lectures. So, approximately here equal lectures here. So, our so teaching, of course, so there are books available for this. You can always teach from following a book and so on. So, what is the idea of this lecture, this meeting that we are doing? Basically to say how to start teaching and how to motivate the students who are coming from school, right. In a school, they are just told this is the formula, you do it, this, and they just come with a mindset, and so they really don't know why we are doing whatever we are doing, and I am sure we all have been through that phase of life, right. And we like if someone tells you why we are doing whatever we are doing, right, and that is very important, which is the motivation part of it. So, I am just going to describe, I mean, how I would take this course, how I would start this course, and how so how I teach these courses whenever I teach these courses. So, for instance, in the first semester we start with real numbers, the basic stuffs, right. Now, real numbers everyone knows what is that big deal to teach. So, the first thing that I always tell any of my students, I mean, whether you are going to do research in your life later or not, so regarding mathematics. So, people say there are lots of open problems, unsolved problems in mathematics which we have not done, but according to me there is only one unsolved problem in mathematics which we have not done, and every other open or unsolved problem is related to that one unsolved problem, which is infinity, right. We do not understand infinity, and there are various ways of understanding, I mean understanding or describing infinity. Infinity is something which we can't assimilate in our mind. All we see things around are mostly finite stuffs, or we kind of assimilate it as a finite stuff. So, even though that is infinity. So, this feeling of infinity has to be given to students. That is the one major problem of mathematics. Anything that you do, ODE is a problem, PD is a problem, it is something to do with infinity of functions, so some limit process happening there, which is infinity, right. So, there is only one open problem in mathematics, which is infinity. Every other problem that you can think of is related to that one problem, right. And real number system is the first place which you teach, and that is the first place where you can actually talk about infinity to students. So, you can actually tell them what it means. So, how do I motivate these? For instance, someone asked me, why should I mean, I do go to these engineering colleges outside where they won't give, they come and ask me, why are we studying sequences, series, convergence? क्या फ़ायदा है इसका? I mean, all that they keep coming with because they don't understand these things. I don't know. So, do you know the Zeno's paradox? Have you heard of Zeno's paradox? How many of you have not heard of it? Okay, that's a lot. So, that is something that I start with. So, Zeno is, so this is some 2500-year-old story of someone. I mean, he gave some 40 paradoxes. I don't know if this light, I don't know if you can see it. So, what the problem that Zeno posed was this, that so you know Achilles, so there is this Trojan war, I mean the hero of the Trojan war. So, he was a hero there, right, it is like, so he just made a story out of this. So, Achilles and tortoise are going for a race, okay. So, so then they have this argument, right, there is this race between Achilles and tortoise. And then Achilles is very, because he is someone who can fight wars with big people, and tortoise is nothing, and they are just going for a race. He can run faster than race, of course, obviously, right. So, then so they agree for a race, but then the tortoise tells him that I can beat you. Achilles says you can't. Then he kind of gives an argument to Achilles that I can beat you for the following reason, and that argument is what Zeno gives in, and that is a very interesting argument. And after that, Achilles is convinced that yeah, he can't beat the tortoise. Okay. And what is the thing is, the argument is this, that they both want to race. So, think of this guy as Achilles, and there is a tortoise. I just put a triangle, okay. I can't draw a tortoise here. So, they want, so they both want to start a race. So, this tortoise says that, see, you are anyway, So, you can run faster than me. So, give me some start ahead. Okay? I will start ahead of you somewhere, and then we will start the race, and I am sure I will win the race. So, this guy agrees and he says, okay, I give you some start ahead. So, call that distance say x naught. Okay? So, he starts. So, this guy, so this is a place where tortoise starts and this is a place where Achilles starts. So, then and they have a distance of x naught to begin with, right. So, then the way tortoise argues that I will win is that, see, whenever you reach from this point to this x naught point here, I would have moved little bit further, right. So, I am slower than you. So, I would not have taken x naught, but I would have reached some place somewhere, say x 1, which is less than x naught probably. So, when you reach here, I would have gone little further ahead, right, say x 1. When you reach x 1, I would have gone little further ahead, say x 2, right. So, if you so whenever you reach my point, I would have moved from that point little ahead. So, you keep arguing this way, you would have never crossed me, right. So, you would have never crossed me. So, I would always win the race, because you would never cross. This was a valid argument for Achilles. He was like, yeah, okay, I agree that I will lose. But then we know in practical, I mean in real ones, so in real reason, that this guy can overtake tortoise, right. So, what is happening there? How do you, so this was the paradox which Zeno posed. Okay. Now, let me, I do not know if you have done, of course, all of you must have done mathematics courses, right. So, in a mathematics courses you have this. Suppose I have a set, right, which is bounded above, then there is a least upper bound for that set. You all know this result, right. That is an assumption that we make. Why do we make that assumption? To solve that paradox. This sequence x naught, x 1, x 2 that is showing is a sequence of numbers which are going to be, I mean, suppose the sequence of numbers are bounded above, then there is a smallest lower bound, and at that time is when this Achilles will overtake tortoise. So, this is what is called the continuum property of real numbers. And if you remember, I mean, the mathematicians here might know, that is the first property that you are going to introduce if you are going to talk about real numbers. The first assumption that you are going to make about real numbers is that if I have any real number set, if it is bounded above, then it is going to have a least upper bound, right. Why do we need that assumption on real numbers? Because that is what we see happening in reality, and that is the example that I gave you just now, right. So, that is how you impose this continuum property, which is an hypothesis, which is actually an axiom, and under this axiom you derive every other result that you prove in real analysis, everything, right, everything about even the fact that the set of all natural numbers is unbounded. When you say 1, 2, 3, 4 are all unbounded, right, then this is a consequence of these properties, right. All this is, I mean, so there is a reason. So, suppose I start my course like this by telling you this property, and then this is why this is happening, then you do not have to forget it, right. I mean, you do not have to really sit and prepare for an exam, or something. You know what is the assumption, then I know what needs to do, and I just have to work out the examples, right. Similarly, another example for continuum property is this the method of exhaustion, right. I mean, it's similar thing. I mean, suppose I want to find the area of the circle. No, like modern days we have all those methods. So, how did initially people started even thinking of any area bounded by curved surface? How do I find the area for something like these kind of polygons? They could do, right, as length and breadth and so on, triangle, they could do all that. But what about curved surfaces? They were doing approximations, right. They were doing, so they were like approximating. Suppose say I want to find the area of this, I find the area of this, but that is going to be smaller than what I want. So, then I increase it little bit, make another polygon, and forget about this A1 and consider that A2 is this new polygon with 6 sides, right. Just call this A2, keep approximating your region. Now I will have 12 sides. What are you doing here? You are approximating a region by something, and what are you doing here? You are now getting numbers, right, which are increasing, but every time the number is always bounded by this bigger number. This is going to be finite, right. So, that is how the property that, okay, a set you have which is bounded above has a least number, and that least number has to be the area of this circle, and that is how you compute the value of pi, irrational numbers, everything, right. There is for instance, suppose that Zeno's paradox that I talked about, Achilles and tortoise. Tortoise had a start. Suppose for a reason the initial gain that the tortoise gets is 1, and suppose every time Achilles reaches tortoise, that guy has moved only by 1 by n, say here say 1 by 2. When he reaches 1 by 2, this has moved by 1 by 3. If this is the distance which tortoise can manage, then this guy can never overtake tortoise, and this is what you study as the divergence of the harmonic series, right. So, the entire idea of all these things is that you can motivate infinity, convergence of sequences, divergence of sequences, all via these kind of connections that you make, which will help them understand why we are doing whatever we are doing, right. Another example which we give for the convergent sequences is something which is the bulldozer and bee story. So, there are two bulldozers approaching each other. Okay. Imagine that the bulldozers are say 1 kilometer apart, okay, and there is a bee sitting on one of the bulldozer, and it can move only between the bulldozers. It can't move, fly anywhere else. Maybe it's a stupid bee, we can assume that. It cannot fly somewhere else, it's just flying between them, there is no other space to fly. So, suppose I ask, and then the bee is flying say at a speed of 2 kilometer per hour, right. What is the time that the bee will get crushed between the bulldozers, right. Now, this question looks, I mean so this was actually asked in some tea party of when von Neumann was somewhere and so on. But the point here is, I mean here if you actually really concentrate, you do not have to worry about the speed of the bee, how fast it flies and so on. It will get crushed whenever the two bulldozers meet, right. But someone who does not see this, and when will they meet? Since they are both moving at the same speed, they will meet at the halfway. So, exactly at the halfway they are going to get crushed, I mean the bee is going to get crushed. Simple answer to this. But suppose I had given you this and you did not have this hint, what would you do? You would start computing using the speed of the bee, using the distance, I mean speed of the bulldozers, start writing something. I am just giving an example, right. If you start writing something, what do you get? You will get a series, right, and that series should converge to the half number, the number where the bee will get crushed. So, these are some things which you can add to your mathematics course. I do not know if this is how mathematics was kind of taught to you, but if you add these things to the course, they have a relation with the real world, they know what is happening. So, then they can connect the, I mean textbook results to what is there, and they do not have to really remember something or mug up something, right. And there is another interesting result about infinity is this Thomson's lamp. How many of you know about this Thomson's lamp? So, he gave something about, I mean how infinity is still a problem. So, assume there is some what can we call some super creature or some god like creature if you want, right, who is very good at doing something. So, what problem he posed was this, that suppose there is a lamp which is on now, okay, and I have the control of the switch, right, or to on and off. So, exactly after 1 minute I switch it off, okay, and then half minute later, so exactly so at 0 minutes the lamp is on, after 1 minute I switch off the lamp, and then after half a minute, that means after half a minute I switch on the lamp, and then another for a minute, I switch off the lamp, and so on. If I keep doing, suppose, and here you see practically there is a problem. I have to be so fast to really switch on and on of the lamp at half of the previous time, right, which is why I am assuming a godlike creature who can do that, right. Suppose I can do that, right. Now, what about this series? This series is going to converge, you know, right. I mean, if you do this, suppose assume you have done this course. So, this series is just 1 over 2 power k kind of series, which is going to 1 with k 0, which is going to converge to 2. This series is going to converge. So, his problem is, okay, since you are saying there is an infinite thing which is going to converge, I am posing this problem that I am switching on and off at every step of the series. Okay. At the end, since you are saying it is converging to a finite number, right, will the lamp be on or off at the end, at the infinite process? Why? Because every time you have on, there is another time where you are going to off it, switch it off, and every time you have switched it off, there is another half time of that where you are going to switch it on. So, at the end of the process, you are going to have the lamp on or off. Both are not the answer. Okay, let me rephrase. Okay, so that's a very good motivation for oscillating sequence. You see, so let's say every time I mean the lamp is on, I denote it as 1. Every time the lamp is off, I denote it as 0, binary, right, on off, right. I can do this. So, which means what you are asking is there is a 1 0 1 0 1 0 infinite process. At the end, what is it, 1 or 0? But yeah, but just now you all said it's on, or just now you said you are it's off. Why 1 by 2? No, that is probability, on or off. You are saying I don't know if it's on or off, but the probability of being on is half, probability of being off is half. That is taking an escape route. Of course, that's what we do finally. Okay. And anyway, what is that 1 by 2? If you know what is called Cesaro sum, that 1 by 2 is an answer coming from the Cesaro sum of infinite series. Okay. And this is nothing but the oscillating sequence of the Cesaro sum. And here there is an interesting, since I have started with 1 0 sequence, let's say I take this sequence, right. In fact, every time you I mean every time, so the first term is 1 after I sum, suppose I sum up to this, So, after the second term the sum is 0, after the third term the sum is 1, after the fourth term the sum is 0, and so on, which is going to give you that state of the on off lamp of this situation, right. This is divergent, fine, but right. Now, what about this series? Yeah.
We are reducing the time. So
yeah.
We cannot say after a long time, the time will end very fast.
Yeah, that's what I am saying, it is converging, that series is converging.
So, at the, what does it mean at the end?
At the end is, that is what the Thompson's question is. He is asking, you are saying this series converges. So, he is asking from a, so think of this as a schoolboy question, right. Someone comes and tells you that this series converges, right, which is an infinite process, but you are finally saying it kind of converges to 0. So, what Thompson is asking is, suppose there is a creature who at every instant of this time is switching on and off, and since you are going, and then since you are saying this is going to converge somewhere this is going to stop. So, at some situation the lamp has to be on or off because it is a converging sequence. If I am doing the same process in this time, say 1, 1 by 2, 1 by 3 and 1 by 4, then this is divergent series, I do not have to ask this question at all, it is fine. But he is asking this question, I am not doing at this time, Every time I switch on and off, half of the previous time, and you are telling me that that series is convergent, right. That means there is a finite number after that. That means there is a finite state. So, at that state is the lamp on or off? That is a valid question, right. That is the problem with infinity, right. And it is not a problem with infinity, it is how we understand infinity. Infinity has different natures. So, it does not fit into our notion of how we behave. We always work with finite things or approximation of finite things, and right, that is how our mind thinks, right. So, this question is a valid question. He is asking that. So, these are all still paradox. You can't. So, the only answer to Thomson's lamp question is the fact that he is assuming a creature who can do this is not possible, is the kind of answer that you have for the Thomson's lamp question. But these are good motivations for your convergent series, oscillating sequences, divergent series. And how do you define convergence of series? By the convergence of partial sums, right. Why so? For instance, whatever he said about half, I can get the limit of this as half. For instance, this rearrangement of series, right. It is not always true. If you have done the only for for non-conditionally convergent sequences, you cannot do this rearrangement of series, right. For instance, suppose I have this series, I can rearrange this series like this, right. Right, I can rearrange it like this, right. It is the same series. I am just looking at the series in a different way, right, and every time this is 0, right. After that means the limit of this should be 1, right. So, this is 1, limit of this is 1, right, but I can rearrange the same series like this. Every time this is 0, same series 1 equal to 0, right, not possible. That is what tells you that, but if I have two numbers 2 plus 3, I can rearrange 3 plus 2 commutative, no problem, 1 plus 2 plus 5, 5 plus 1 plus 2, no problem. Whenever I had finite, I had no problem, but when I have infinite, I cannot rearrange, I cannot put them back. That is a problem, right, because if I can do that, then I have some contradiction. How do you fix these things? The course tells you what to do, right. So, it tells you what to do. You cannot rearrange an infinite series. In fact, there is a Riemann rearrangement theorem, which we usually do not do it at this level courses, which tells you that if you have a sequence which is conditionally convergent, then so you can always rearrange a series to get whatever number you want. That is his theorem. It tells you that suppose I have an infinite series which is conditionally convergent. Conditionally convergent means that mod of a n is not converging, but a n is converging, okay, it is converging. If you have this situation, then you can always rearrange this series to get whatever real number or even infinite number that you want, right. That is again a problem with infinity, right. So, you can motivate these kind of stuffs when you do say real number sequences, series and so on. And what about continuous function, and then you slowly move to from numbers to functions, right. And once you go to functions, you will get into continuous functions, derivative, you all must have done because you are all engineers, right, continuous function. What is the definition of continuous function that you know? You do not know, eh? Limit exists? That is actually a consequence of. I can see that. I can see the engineer's definition here. You see, all the definitions that you are giving are all consequences of continuous functions. See, basically, the thing that one needs to understand is all that what we know today, someone did it because there was a problem. He had some problem which he couldn't solve, and he tried solving it. So, he added some knowledge to the subject, right. That is how we progressed. So, the difficulty that he had, we should take the students to that difficulty, so that they appreciate whatever they are doing is doing. Say 300 years back, 400 back, suppose I had asked what is a continuous function, people have just said this: whatever function that I can draw without lifting my hand, right, is a continuous function. Valid definition, right? That is how even people like big mathematicians whom we think today were thinking of continuous functions. But when they were solving ODE, when your Fourier series came, when they were trying to study these convergence, they started seeing problems. Some things were not behaving the way we wanted. I will come to that whenever we reach that part, right. So then they realized that, because this is a nice definition, right, draw the graph without lifting the hand. But if I want to prove something is a continuous function, how do I prove? By drawing it, right. The second thing is, anyway, that is not the point. So how do I define this, right? How do I define continuous functions? And the other, the second thing was that how did they imagine functions were? They always thought of functions as having some formula, x square plus x plus 3, x square plus y square plus into something. They always had a notion of some equation for the function, right? But not all functions are coming that way. These were also kind of realized at the middle of 19th century. That is when, I do not know if you have seen this definition of, so when we introduce in this course of continuous functions, we do not give the definition of limit of the function x going to x naught is f of x naught, right. What you are saying is this definition: a function is continuous if limit of x going to x naught is f of x naught, right. This one can of course write in terms of the limit definition and so on, but this is actually a consequence of the continuous function. The definition that we give for continuous function is, if you have heard of this epsilon delta definition, which is for every epsilon there exists a delta such that, right, that is the definition that we give. And the natural question that students ask is this: sir, when this works, when this is a nice definition, why are you bothering us with this definition? Something, the same thing you might be also asking me now, right? There exists for every epsilon there exists a delta such that this is less than epsilon whenever does not make any sense, right? Must be some mad person who came up with this definition, right? Right? The guy who came up with the definition was Weierstrass, okay, and he had a reason to introduce this kind of definition, and all this is consequence of that. See here again, when you say, okay, when you say this is the definition of continuous function, I would ask you, what is the definition of limit x going to x naught? You will have a definition. How do you write that?
X minus x naught minus and x minus delta tends to x naught and x naught plus delta.
No, not here. This. Suppose, so you are saying limit of x naught going, x going to x naught f of x is equal to f of x naught. Suppose this is the definition that you want to take. I do not understand what is limit of x going to x naught f of x. Suppose I do not understand. I ask you, what is that? How will you explain that to me? What is the left approaching, right approaching? Huh?
Deleted neighborhood of the x naught.
Deleted neighborhood. See, every time so I am trying to understand something, and you are giving me a more complicated word, right?
If you define for every interval at the time.
How do you define limit of something? Suppose I want to say limit of this going to f of x to L. How do you define that? That is this definition, right? How do you define limit? Somewhere in your mind, at the back of the mind, you have assumed limit, and you have said that any time I say this to someone else, he will also understand what is limit. But what is the definition of limit, right? Because this is just a notation, right? What is the definition? What is the meaning of this? Meaning is this. And what is this? This, the way I write, this is how books will have, right, also have it. But the way I write this, does not make any sense here, right? Does not make any sense here. Now I will explain this to you. suppose I have a continuous function, I want to pick a x naught, I want to show this function is continuous at x naught. What is that saying? That every time, for every epsilon that I choose, okay, and a epsilon neighborhood of f of x naught, this is f of x naught plus epsilon, this is f of x naught minus epsilon. For every neighborhood that I choose, I should be able to get some neighborhood around x naught, which I call the delta neighborhood, such that this triangle that you draw, I mean not triangle, the rectangle that you draw of delta side and epsilon side, right, the graph of the function in that triangle is entering at one place, exiting will not go outside, right, at one place. For instance, if I take a discontinuous function like this, right, if I take this point, this is a point of discontinuity, right, for every epsilon, I mean for every delta I take, okay, I can get a rectangle such that the graph jumps out of the rectangle, right. This is a natural definition to give for continuous function, and for uniformly continuous function you can actually say, and so you can actually say that if I move, so once I fix a epsilon delta, if I move this rectangle along this graph, right, to make any difference, that is uniform continuity, that is this choice of delta does not depend on this x naught, because suppose I choose this x naught, I may not get the same delta here, it could be some delta 1. This could be a different rectangle for the same epsilon, it is possible, right. So, that is how you define continuous, uniform continuous and so on. If you actually explain these things in this way, and then you can derive all these properties, you can derive all these properties from here directly, because this is just the definition, so this is just a rewriting of this form, right. Similarly, you can keep moving ahead. So, we go into series about Riemann integration, right. Why do we do? So, what is Riemann integration? Computing area under a graph, right, and you all might know how to do that, right. There is a Riemann upper sum, there is a Riemann lower sum, you as long as they come, and how do they do that? Again, there is some infinity problem, it is supremum over all partitions. Why are we doing it the way they are doing, right? How do you, I mean it is like counting, right? Riemann integration is like counting. Suppose I give you a bunch of coins, आजकल नहीं है, like 5 पैसे coin, 10 पैसे, 25 पैसे, 50 पैसे, 1 rupee, something. I mean I am just using Hindi, if you do not understand Hindi, pardon. 5 paise, 10 paise, 15 paise, 25 paise, 50 paise, 1 rupee. I give you a bunch of coins, right, and then I ask you to count and give me the total value of the coins. What would you do? You start counting, right? That is what he does. So what does Riemann integration? He is doing partition of the, the domain. What is he doing? Basically, what he is doing, I have some bunch of chalks here. I just separate them the way I want, whatever partition I do, and then I count each partition, the sum. If every time I count each partition, in whatever partition I do, the number should come out as one number. If it comes out as one single number, that is the total value, right? Right? That is how I can do that, right? That is what he is doing, right? Because I am going to try to, because I have a graph, I am just adding these lines, but infinite number of times. How do I do that? That is by partitioning these range. So, I am just taking sum of all these lines, because this now I am doing over an uncountable set. So, here again he had a way of tackling infinity via some finiteness, that is what he was able to do Riemann integration. Yeah.
Actually, I have a doubt. It's not on what you are discussing, but relating with like this between this continuous and a discrete function. So actually, my doubt is, I have read and heard in one class that if it is a continuous probability function,
Okay.
then you can't say, you can't determine probability of a particular value. Probability of any particular value will be 0.
Okay.
But if it is a discrete probability distribution,
Okay.
then you can determine the probability of that value.
Okay.
I heard that class and I heard the explanation also, but somewhere down the line I lost.
Okay, I think that requires more understanding of measure theory, right? You have to understand probability in the sense of measures, right. Once you understand probability, so in sense of measures, you should understand probability distribution in terms of I mean the events in terms of measurable sets, and then one can explain that, but I think that's beyond.
Sir, can I apply that same thing to any continuous and discrete function?
No,
For
see,
example,
for instance, here in a sense when we are doing all these things, we have at the back of the mind a notion of area, length, volume, which is the Lebesgue measure which we think of as. That is probability measure, which is a different kind of behavior of a measure. So you can't apply the same result from there to there, because it's a different measure, it's a different measure here. So here we have assumed that we are working with a notion of length, area, right, which is the Lebesgue measure.
sir, what my thing is, if f of t is a continuous function, f of t is a continuous function,
Okay.
can I particularly pick a value of f of 3 and can I say that is that value of f of 3? Can I say that for sure?
No, I didn't understand. If you have a continuous function,
F of t,
yeah,
can I pick a domain value and determine its range?
no, obviously you can't, right? I mean,
Yes, sir. Domain is, if my domain is, if the value I want to find is 3, the time
Yeah.
value where I want to find is 3.
yeah.
Can I just substitute that in the function's equation and say that this is the value at the 3?
No, you can't. In general, you can't. So when you have measure theory, there is a notion of something, some zero measure sets, like the way in probability they do almost surely and so on. There is a notion of these stuffs which separates these out. In general, you can't do that, and we don't have that situation at all. In general, we can't do that, but of course, we can discuss that maybe later after the class. So in general, we can't do that. Okay. So once I finish Riemann integration, I have completed one dimension. You see, this entire course, if you see, has been divided into two parts. As I said, 20 lectures, 20 lectures. The first 20 lectures was just one dimension dealing with, right? And the next 20 lectures is about higher dimension. And you can very well say that we need all these things even if you have to become an engineer, right? You need to know these stuffs to even to work as an engineer. So you have to introduce these things to even to an engineering student at that level, so that he understands. Okay. What else? I think let's then move to the. So this is the first semester course. Now I move to the second semester course, which is like, so there we teach linear algebra, which is for some 20 lectures, and then we do complex analysis, which is again for some 20 lectures. Okay. So there again, if I have to do linear algebra, the question is always why we are doing linear algebra and so on and so forth, right? So you can motivate the system of linear equations even from mathematics side, which usually you would know, or even from engineering side you can talk about the current flow in a kind of electrical network, the traffic flow at junctions, because all these are problems which will give you a system of linear equation which you want to solve, or the chemical reactions of balancing chemical reaction, like I mean you want to know how much molecule reacts with how much molecule of something else to give so many molecules of something and so many molecules. That number of molecules you don't, I mean you know, right? I mean if something is burnt in air, that means it's kind of mixing with oxygen and then it's producing something else. What you try to do there actually, you just put something, you burn something. Now how much, so what is the minimum molecule that I should use to really get that result, right? These problems, if you ask these questions, they all boil down to system of linear equation which needs to be solved. Okay. So it's important to introduce the system of linear equation like that. Similarly, when you reach determinant, most of the people don't understand the geometrical notion of determinant. I mean you should tell them that the determinant of a matrix is nothing but the volume that you have if you write down the column vectors, right, draw their region bounded by the column vectors, and that is, and the determinant is nothing but the area of that, right? Right, you understand that, right? Suppose I take this matrix. What is the determinant of this? 1. What is this? This, if you represent the 0 1 vector, sorry 1 0 vector, and 0 1 vector, okay, area of this region. If you have some other vector A B C D matrix, right, you take that vector, area of this parallelogram. Determinant gives you that. In a sense, where is determinant coming? So, linear algebra, any matrix is identified as a linear transformation from Rn to Rn or Rm to Rm, which is why it is an M cross N matrix, right. If you have a linear map from Rn to Rm, then this has a matrix form of M cross N, right. So, any matrix is thought of as a linear maps, right, and what are linear maps doing? Linear maps are doing taking kind of elements of Rn and vectors of Rn to vectors of Rm. That means a region in Rn, suppose this you imagine as Rn and this you imagine as Rm, this region, so some region here gets mapped to some region here, right. For instance, right, for instance, I can map 1 0 0 1 to the region 2 0 0 2, which is precisely the map 2 times identity, right. So, determinant of this is 1, determinant of this is 2. What is determinant of a matrix saying? It is saying when a region gets mapped to another region, right, what is the volume distortion that is happening to that region under the map, and that measurement is given by the determinant of the matrix, right. One should explain these things geometrically, it will give some kind of idea to the student what is happening, and the sign of the determinant is going to tell you whether the orientation is preserved or not. Vectors have orientation, right. If this is A comma B, this is A minus B, right, this is minus A B. So, the orientation changes with sign. So, the sign of the determinant tells you whether the map is preserving the orientation as well. So, positive sign says the orientation is preserved, negative sign says the orientation is not preserved, right. These things one can explain in the say linear algebra course, and of course, eigenvalues, eigenvectors, something which you can't avoid, and then you move into complex move into complex numbers and complex analysis. Again you should tell them, the natural question is, why are we studying complex numbers? Why did someone imagine a number I? Huh? Negativity? Sorry? Yeah.
5. We are squaring 5, then we get it 25.
Yeah.
Minus 5, we have get it again 25. So how these two things have been limited? That is why complex number, that is incorporated I.
No, I mean, for instance, I know this result in real numbers, right? That if I take any real number, x, then x square is always greater than or equal to 0. Right? We know this. This is a theorem that we know. By introducing a I, right? What are you asking? What is the number? What is the number such that x square is minus 1? That is what you are asking when you are introducing, right, a number. Why would I ask this question when I already know the square of every real number is positive? I have a result in real analysis tells me that if I square any real number, it is always going to be a positive number. Then why would I ask this stupid question, what is the number whose square is minus 1? पूछना ही नहीं चाहिए ना ये, right? I shouldn't be even asking this question. But we do ask, we answer that, and we do an entire course, trouble ourselves, trouble students.
That minus does not represent sign, but it represents direction.
Square number, what direction here? Real number, what is the direction? whatever is the direction. Square, does it imply anything to do with direction?
No.
Squaring.
But whenever you take a complex number, it becomes a vector. So
Complex number, I mean, after you do this, you have that notion. Suppose you go 500 years before, you don't have complex numbers. Someone first asked this question that I want to introduce this. Why would any sane person look for a number whose square is -1 when I know already that the squares are always positive? I shouldn't be even asking this question, right? उसका solution नहीं है. See, right? Ideally the solution should not exist. What is solution of, see, what is x square plus 1 and so on? X squares are parabolas, right? Parabola, right? So when you say x square plus 1, it's a parabola with an intercept 1, right? At x equal to 0, it's 1. And when you say solution to that, what does it mean? What are the zeros, or where does it intersect the x axis? Where does it become 0? That is what solution means. So x square plus 1 has no solution. You already have an answer for that as well. So why should I ask for x square plus 1? Why should I solve this equation? I say there is no x which solves this problem, because there is no x where it intersects. Most of us do not know why complex numbers are introduced.
We have two different type of quantities,
Ah.
and we want to incorporate them in the same equation,
Hmm.
but we don't want them to be mixed.
Okay.
So then we can use this kind of thing.
No, I don't understand. You have two quantities, you don't want them mixed. So,
Like for example, you want pen and two pencils.
uh,
Okay, so you just want to make one equation only,
but what will you make equation out of pen and pencil?
like 1 plus j2, like this.
What are you trying to do here? Huh? Sorry? So how does this relate to x square minus 1? I mean, doesn't make.
Now it will be easier for us to use this kind of analysis for this problem.
Oh yeah, but I don't see the connection. I mean, I don't see how writing two pencil and say one pen and two pencil with a complex number, and what equation is going? What is the? I mean, how do you relate that? I mean that's how it came. Huh? No, but this is, yeah, but see, what you are all doing is that you have already accepted these things. It is there because we have never questioned it, right? Now, since we know something using that, we are trying to go back from the application of there, right? एक पेंसिल रिलेट करना, एक पेन और दो पेंसिल क्यों रिलेट करना है मुझे? Unless it comes out naturally. कहाँ आया ये problem? Like where did it come? Right? These are all, right, and issues, right? How do you answer these questions? We need to tell these to students because they have the same thing, right? I mean, even when I was like you, that's the same question. Why are they teaching us this? I don't even understand. I know that x square is positive. Why would I look for x square equal to -1? Kind of questions. And all this came naturally. Complex numbers came basically an extra space. I mean, think of like this. I am standing here, someone has built a wall both sides of me. The only direction I can move is front or back. Until 1500 years we were doing this, right? But there were many stuffs which was practically happening in front of our eyes. We were not, so we were unable to study those things, and to understand those things it was important I move in the other direction as well, and that wall had to be removed, okay? And that wall that was removed was this complex number. It was just a convenience sake. First complex numbers came as a convenience just to solve algebraic equations of say even say cubic equation and other 4th degree and so on, 3rd degree, 4th degree equations. You cannot find solutions, I mean real solutions of cubic equations. For some of the equation you cannot find the solution without going to complex, without solving that x square equal to -1. Till date there is no other approach. It was just an extra space. So I basically move there, do whatever I want. I have now kind of free space now. I kind of relax my hands and then come back and then come back to real solutions again. That is how it was introduced. Then similarly, it moved into functions. Like when we do this Cauchy-Riemann equations, all are related to harmonic functions, right? They were trying to understand the solutions of harmonic functions. That is how complex numbers became complex functions and so on, right? Holomorphic functions and so on. So this way you can motivate and yeah. So I don't know how much time we have. Yeah, I will just finish with this. So then at the third semester we move to ODE, PDE and so on. So how do you, so you have to motivate ODE, PDE, you can always do it because now you are all engineers, you understand, I don't have to elaborate on this, how to motivate an ODE equation, PDE equation. The moment you had Newton's second law, you had the first ODE. The moment D'Alembert studied vibrating strings, you had the first PDE. And then everything, and in fact entire Fourier series was developed out of Fourier study of heat equation, right. In fact, you will not, you are all engineers, you should appreciate that the entire mathematics that I talked about before, answers like these questions, all these, if you hate these kind of definitions in mathematics, you should go and hate Fourier, okay. His work on heat equation is what started the entire questions for an entire century of mathematicians about what is a function, what is convergence, right, what is uniform convergence, when will something happen, when will something not happen. All these started with Fourier study of heat equation and all eigenvalue problems. So you saw eigenvalue problems in linear algebra where it was about matrices, numbers, right. Here you are going to study eigenvalue, so this term level problems that you see here, these are eigenvalue problems for differential operators, okay. How does that naturally come? That naturally comes from separation of variables, which they introduced to solve these, and all these were guesses, right. It was just a guess, right. I mean, so I want to find a solution, I will assume that the solution's variable can be separated. Why would you assume that? You have to justify that, but you do that. Why do you do that? But and the student will ask you that, why are you separating variables when you don't, whether it's, I mean, so what if I cannot have a solution like that? Then you show them, yes, you cannot, because there is a uniqueness result for all these equations. If I have a heat equation satisfying some boundary conditions, there is only one solution. And if some hook and crook I can find that one solution, then I am done. Only if I cannot find. So if I assume separation of variable, if I have kind of get hold of a solution, by uniqueness I know that is the only solution. So you actually have a good logic there to circle there, right. So we can do all that here in the ODE PD course. A very good motivation is this method of characteristics, which you have to really motivate for first order equation. How do you get the solution of first order PDE? So you think of that as a surface, you are going to get characteristic curves along this surface. What is characteristic curve? That curve along which u is constant or known, and I take union of all these curves, which is going to give me a surface, right. These are the ideas that you should impart when you teach these kind of subjects here. Similarly, the classification of second order PDE, that is natural, the way you have in algebraic equation, similar results get applied here. So the second order PDE gets divided into elliptic PDEs, parabolic, hyperbolic, like wave equation is a hyperbolic, heat is a parabolic, right. Laplacian is an elliptic equation. How do you get these distinctions, and what is important of doing these distinctions, right, because of the solutions. All this you can teach in a course when you are, so if you add these things in your course details, then that will make the students, I mean, aware that okay, there is a reason why we are doing whatever we are doing, and that is important to keep them inside the course for the semester, right. I think I will stop here. Thanks.